Dear students, welcome to another day's lecture on elements of machine design. Yesterday we have seen about the screw jack. Now here is a drawing, a details drawing of a screw jack. You see how you draw it. You see, this is the body, the first part. When it is cut in section, it will appear like this. The body tapers as it goes down. Then the second part is the nut. Nut has a collar here so that it can sit uh, on the body and it fits here. So this inside diameter and this outside diameter should be same. It will be normally a press fit at clearance fit. Okay, but here we could have provided a grub screw that is not shown here. Okay, now the third part is this one. This is the screw spindle. You can see there is a head here and there is a little projection. Okay, and there is a tapped hole here. You see, this is a tapped hole into which this screw goes. And before the screw is put now, see, upon that we put the washer. As we put the cup, and in the cup they will put a washer. See, and this diameter inside should be the same as this diameter, so that it fits here. The cup is shown in two views, the front view and the top. In the top view it looks like this. Okay, so the third one is this, fourth one is the cup, fifth one is the Tommy bar. This is the Tommy bar, and sixth one is the washer, and seventh is the screw. Okay, each is only one part is needed, no two parts needed. Now let us see the animation of this. See, there is a grub screw 7, that is the washer, and there is the cup, and that is the Tommy bar, and there is the screw spindle, and that is the nut, and this is the body. Okay, now today we are going to discuss about the design of the toggle jack. You see toggle jack, how it looks. See, this is the toggle jack. See, see, these are used for rotating the screw. See, toggle jack is like this. Okay, let us come to the design of the toggle jack. In the toggle jack, you see there is a base here, and there is pins here. You see there are a number of pins for joining. Okay, and then you see there is nut here inside. You are seeing here there is a nut provided here and here. So in this nut there are there is a rod on which threads are cut. Hmm? On one side left hand threads, on one side right hand threads, and there is a stopper provided here and nut. And this is, if you show like this is means this is made square, it is not circle, so that our spanner or something can fit. Okay, so, and in the this side also then there is a hand screw here, and there are links. These are all links. This is one link, two links, three links, four links, and these two are nuts. This is a screw on which on one side there is left hand thread, on the other side right hand thread. That is how this toggle jack is. Weight comes on the top. Okay, and nowadays most of the cars they have the toggle jack only, not screw jack. Screw jack is used for heavy applications like trucks, buses. If you want to use in those things, you use screw jack. Toggle jack, if these small cars which we use, they're all being provided with the toggle jack only. Okay. Okay. Come to the design. Design of screw. Say, say the total tensile force on the square threaded screw is W1 into 2 times of force. See, this W is the vertical force that is acting here. That means that is the weight of either the car or any other load that you are lifting. See, here we can see each nut carries half the total load on the jack. See, suppose on one nut, how much W is coming? W by 2 is coming. So because of this W by 2, okay, which is acting in this direction, this link is CD, and this is the square threaded screw. So this square threaded screw is being exposed to this force F. Okay, so this force F, uh, this is because of W by 2, and similar pull will be there on the other nut also. So therefore the total tensile load on the square threaded rod will be 2 times of F. See, total tensile force on the square threaded screw will be 2 times of F, and that we are calling as W1. Okay, see, the W is the load of the car or whatever is put on that, and the W1 is the total tensile force on the square threaded screw. Okay, so you see, now what is this F? You see, F is from this diagram. See, if this is W by 2 and this is F, from that this is angle theta. Now F can be written as W upon 2 tan theta. Okay, so direct compressive stresses are induced in the screw due to application of load W. Okay, and that, see, sometimes it is compressive, sometimes it is, so therefore Sigma C can be the total load coming upon the threaded screw, square threaded screw, divided by the cross-sectional area. Cross-section will be minimum at the core diameter. So we use core diameter. Okay. And from this you can find out what you can determine the core diameter. DC you can find out because W1, if W is known, then F you will know. If F is known, if W1 will know. If W1 is known and sigma C is known, you can find out DC. In addition to the compressive stress, the screw is also subjected to torsional shear. See, just like the screw jack. In the screw jack also, first we have designed on the basis of the compressive stress that is coming, and then we have considered the torsional shear stress because of the rotation, torque that is given. For this, increase the value of core diameter referring to the standard core diameter DC, referring to the standard table for screw threads, and again determine the core diameter. See, for that diameter DC, whatever, suppose if it comes 20 or something, you increase it. Okay, maybe take some 30 or more than. And then once you determine DC, final DC, then to go and see in the table what will be DO, what will be pitch, out nominal diameter, pitch, all this, and what should be the mean diameter. Mean diameter can be found out like this also with this equation. Okay, then the torsional shear stress induced in the screw, we have this formula. T is equal to pi by 16 tau d cube. So from that, shear stress is 16 T upon pi dc cube. Okay, and we have this formula that we have seen in the screw jack when the power screws while lifting. Okay, that is T is equal to W1 into tan of 5 plus alpha into dm by 2. Okay, so from this, you see here for substituting T, here to get T, you need this equation. From this equation, because you know W1, if you know the friction angle will be, you see, if you know the materials, the nut and screw materials, if you know, you'll be able to find our friction angle with the from the standard tables. And if you know the alpha, that is the that is the what is the angle, that is the helix angle of the screw. If you know alpha, you know the dm, so you will be able to find out t, and you substitute here, then you will have tau. So now you have sigma c and a tau. When sigma c and tau both two are there, now one is sigma stress, another is tau stress. What you can do is tau maximum you can find out, and sigma c maximum you can find out. These two you can find out, and you have to check whether these things are within the permissible limit or not. Okay, then next you have to design the nut. When we are designing the nut, the threads of the nut and the screw, they are engaged to each other, and there is relative motion between them. So because there is relative motion between them and they are under compressive load, then they fail under bearing pressure. So bearing pressure formula we have. This is also much similar like the screw jack design. You see, what is the load coming? W1 is coming. It's not W. W is the load the car is being, the car load. W1 is the load that is coming upon that. Okay, that threaded rod. Okay, and this is the area of failure. This is the projected area. See, from the top view, when you are seeing, it is like a donut. That means what? A circle with a hole in the middle. Then what will be the area? Pi by 4 do square minus dc square. And how many threads will be meshing? N number of threads will be meshing. Okay, so this will be the total area. So from here you will get see, bearing pressure, if you know W1, you know, you will get N, because DC, DO, these also we know. Okay, so the number of threads engaged in the nut n is determined by this equation. Okay, and then the um, okay, see, this is the formula. Once you know what is the number of threads in meshing, that means number of threads in the nut, multiply it by pitch p. Okay, so pitch p is, actually the thickness of the thread is pitch by 2. So one thread will be there, one gap will be there. No, totally it will be p. So p into n, this will give you the height h. Okay, see here the thickness is given p by 2. So number of threads engaged with the nut n is determined by this equation. The height of the nut can be calculated by this. Okay, then design of the pins in the nut. Some pins are there. Okay, pins, no. uh, Say if supposing there are two pins and the cross-sectional area is pi by 4 d1 square, so they will be cutting in shear. So sorry, this is double shear. Okay, because of double shear 2 is coming. So if the pin is getting cut with the force F, so shear stress is F upon double shear, so 2 into pi by 4 d1 square. So from this equation you can find out d1. This pin is not a big deal. What uh, what was needed to be designed was your screw and the nut. Okay, once you screw and the nut, if you have designed, that means you have done the work. Okay, so that's all. I see it is this much similar, as far as the nut and screw design is concerned. Okay, but other things design is not there in the syllabus specifically. They have mentioned it is limited to the design of screw and the nut. So we will stop here. See for the toggle design. Okay. Okay, let us solve one problem each for a screw jack and for the toggle jack. See, here is a question. A screw jack carries a load of 25 kilonewtons. And if the coefficient of friction between the screw and nut is 0.15, design the screw and nut. Neglect collar friction and column action. See, for this always will be given. Neglect collar friction column action, because they were supposed to ask you only for screw and nut design. Okay, then take sigma c 42 Newton per mm square and tau is 30 Newton per mm square for screw, and take tau of nut is 20. See, tau of screw is 30, tau of nut is 20. That means both are made of two different materials. Okay, the permissible bearing pressure PB is 14 Newton per mm square. Okay, and use single start thread. You always assume to be single start thread. Multi start thread and all, we will not be designing at this stage in your diploma level. Okay, so now W is 25 kilonewtons is given. The coefficient of friction mu is 0.15. Okay, and sigma z and all these things are given. Okay, now first is design of screw. So when we design of screw, see, we will be considering pure compression. So pure compression sigma c is a load upon area. You see, area is pi by 4 dc square, because dc, see, among the three diameters, dc is the least in case of screw. In case of nut, it will be do. Okay, so from here you can substitute all the values and you will get dc. So dc, you're getting something 27.52 or something, but this is less. Less means what? This is considering only the compression now, but on the screw, twisting moment also is coming. So a greater value than this 27 we should take. Okay, now here selecting a higher value of core diameter, considering square threaded nominal series of dc 30. You see, where 27 came, we are taking 30. See, now you may say how much more I should take, how much. You see, This may differ. So somebody may take DC 30, somebody may take DC 34, something like that. Okay, doesn't matter. Okay, so for this, no, um, from the chart you will get what is the pitch. Otherwise, no, you can see the chart. For square threaded charts, not many things will be there. From some 30 to 50, from 20 to 50 diameters. What are the different pitches you see? Yeah. Okay. So that you can remember also. Okay, because you will not be allowed to take the charts. Okay, this you have to see in your books also. It may be given. Okay, and you say take what is pitch. Pitch is 6 mm. So now DC is 30, pitch is 6, and DO will be DC plus pitch, that is 36 it will be. So the mean diameter will be between these two. One is 30, one is 36, means it should be in the half. Anyway, for that also there is a formula. DO is equal to mean diameter DM is equal to DO minus pitch by 2. You'll get 33. Okay, now let us come to this helix angle. Helix angle is pitched by the pi d. Tan inverse of tan phi. Tan alpha is pitched by pi d. That is alpha is equal to tan inverse of pitch upon pi d. And from the calculator you can put in OP. This pi is 3.14. D is whatever you got. Mean diameter. You put mean diameter here, not core diameter, and then from that you will get 3.31. And mu, the coefficient of friction mu is equal to tan phi. Okay, otherwise phi is equal to tan inverse of mu, that is tan inverse of 0.15, and that you will get. This is 3 degrees, 8 degrees, and this is 3 degrees. Which is more? Friction angle is more, helix angle is less. Are you seeing? Friction angle is more means what? This is a self-locking screw. Okay, if this is more, this is less, then it will be overhauling screw. Never mind, I'm only saying, uh, to identify which is the self-locking screw and which is the overhauling screw. Okay, then torque required to raise the load will be, you have this formula, T1 is equal to W into tan of phi plus alpha into D by 2. You put all these things, you will get value. You will get the torque value. Okay, and anyway, collar friction, you see why always we are using T1, because there is something called as collar friction also, which is given by T2. So, but for our diploma level, for your syllabus, they have said you neglect all these things, so consider it to be 0. So only T1 we are considering. Okay, now what you have to do? Now you check whether the screw that you have designed is safe in compression and tension, or in the principal stresses. Okay, so you have two stresses, one is compressive stress, one is shear stress. Compressive stress formula is load upon area, that is this much. Okay, and shear, you see this we have done before also, but at that time no, we have taken it as 27 power something, we got it here, but now afterwards we increase the diameter, therefore you calculate again. Okay, so this comes to 35 point something. The shear stress also, you see, because already T1, from this you calculate. And here now when we are using, here you use DC values, because these are the design equations. Okay, whereas uh, here for calculating alpha, here you are using mean diameter. Okay, these are the core diameters here. Okay, so two values you got. After getting those two values, what you have to do? You have to find out two stresses. What is sigma C? Maybe that came to this much. One step is missing here. So see, maximum principal stress you find out, and this is the tau maximum for you find out. If both of them are less than the uh, less than the design less than the permissible stresses, therefore design is safe, you can conclude. Now come to the design of nut. Okay, this is design of nut is designed on the basis of the bearing pressure. So bearing pressure is load upon area, load upon area. One area is the, this is in the top view. If you see a circle with a hole, this is the area, and like that there will be n threads. Okay, like that. So this will be the area. So from that you will get n is coming to some fraction here, 5.74. So you'll make it round figure. 6 threads. If 6 threads are there, pitch is 6. So 6 threads and the pitch is 6 means, you will get the height of the nut is as 36. Okay, so now the height you have got. Then what you have to do, you have to consider the shear stresses induced in the nut. See, uh, um, shear stresses induced in the nut and in the screw. Okay, first, you can find out about the nut. When we are using nut, DO you will use. When you are using for when you are finding out for screw, you will use core diameter, because core diameter will give you the minimum area for the screw, and for the nut, outside diameter will give you the minimum area. Okay, so you take like this, dot pi dot n. This will be the area of shearing. You see, actually pi do into t will be for one thread, and like that you are having n threads. T is the thickness. T is nothing but pitch by 2. So okay, you substitute all these values and you'll get some shear stress, and this shear stress should be less than the permissible or allowable shear stress. Okay, but how much was that permissible stress? See, in our figure question that is given, question for nut how much was there? 20, whereas for screws 30. It should be like that. You see, for the nut when you are designing, uh, no, for nut when you are designing, this should be less than 20 and this should be less than 30. Okay, this is coming less than 20, so design is okay. Similarly, shear stress induced in the screw, you find out. Here again the formula is pi tc into t. This is for one thread and n number of threads in meshing. Meshing only you should consider. Actually, if you say a screw is a long screw having lot of threads, but all are not having, all are not exposed to the shear stress. Only those which are in contact with the nut will be exposed. Okay, so like that you calculate, and then you will get a tau s. Okay, so you say that this is safe now because this is less than 30. So sigma tau s is less than tau allowable. Tau s is 14, tau allowable is 30, so it is less. So design is okay. So you can say the screw is safe against shear failure. This much only you have to design. Okay, so come to another problem. Now this problem, um, yeah, design of a toggle jack which is used to lift 5 kilonewtons. This is W. The jack is operated by means of 400 long lever and 8 symmetrical links are 125 Design, screw and nut. If permissible, tensile stress is 100 Newton per mm square and bearing pressure is not to exceed 20 Newton per mm square. Take coefficient of friction 0.5. Assume the pitch is 6 mm. Okay, now let us see what is all given. W is given 5000 newtons. Okay, sigma T is 100 Newton per mm square. Length of each nut is 125 mm. There are 8 symmetrical nuts. Okay, even the nuts they are considering the base and the top head also they are considering as a link. All are symmetrical, all are of same size, and they are 125 mm. And L is the length of the lever, which is 400 mm. This is the bearing pressure PB, 20 Newton per mm square, and pitch of the threads also is given as 6. Okay, and in a coefficient of friction, that is mu is given. Mu is nothing but tan phi, that is 0.15. This is given. Now, uh, okay, now this is the this. Now you can draw this triangle like this and show that this is the W by 2. The half of it is coming on the nut which is here in this place. Okay, and then this is W by 2, and each link is 125 mm. They said, did they not say link is 125? Yeah, 125 they said. So this link is 125 mm, and then uh, 1 minute. Okay, see here the link is 125 mm, but you know when you completely bring the when you close it, you see still this 125 mm will become almost horizontal. Almost horizontal, it's not exactly horizontal. You see, when this jack is in the bottom position, okay, that is when they say maximum load is coming on the square thread. Okay, so in the bottommost position, say though it is 125 mm, so it can close only like this. Still some out of the 125 mm, 15 mm it is unable to close, because you know these links also have some widths. They cannot be completely coming, and this line cannot overlap here. Okay, so 15 mm here remaining of the 125 mm, that is 105 is remaining. No, that is here. So like this it is there, and you think it's okay. So this theta is taken as 35 mm. See what are they saying here? The jack, and when the jack is at the bottom position, the maximum load is on the square thread. So the position of the CD in bottom position is shown in figure. This is the, you know, whatever is shown is the bottom position. This is the bottom position. In that bottom position only, this theta is taken as 35 degrees, and this is the bottom position. Actually when this is rotated and it comes, you know, it will go to almost it may be even 80 degrees like that. So the bottommost position, this becomes 35. Okay, 35 you take, you know, you take how will we know means you take it hereafter, you use the theta as 35 degrees. Okay, and then okay, now we'll come. You see, this is the force F. This is W by 2. So now you want to find out the formula. The F is equal to W by 2 upon tan theta. Okay, in unopened condition, the maximum theta, um, maximum value of theta is 35 degrees is taken. Taken means it is taken normally. Okay, each nut carries half load, that we have seen, half load W by 2. So the link is subjected to tensile stress while the square thread is under pull. Okay, uh, when it is under pull, it is tensile stress. When it is under compression, that compressive stress will be there. Okay, anyway, if you find out W by 2 is 5 into 10 cube upon 2 into 10 35, that is this value you will get. Okay, a similar force is there in the other nut also. Okay, so the total force is 2 times of this, 2 times of F, and this we are calling as the earlier one. What did we call? If we call W, hmm, yeah, here we have called this W. So now what we are calling this should be W1 in that case. This is W1. So this W1 is 7,400, 7,142. You see how much is that was that W? You see this W is 5,000, whereas this W, whereas where are we? Yeah, this, oh, this W1 is more than that, more than that. So much of load is coming. Okay, anyway, never mind. Okay, consider screw is under tensile strength sigma t. You will find you can find out DC from this load upon area. So you will find out DC came to 9.53, and after finding this, um, What you should do, you should say it is also subject to twisting moment. Therefore we will increase this value of 9.53 and we will take a higher value 14. This is a few mm you take more. You see 9 came or rounded to 10, 10 you rounded to you increase to 14 or something. If you increase to 16 also doesn't matter. Okay. uh, then the nominal diameter DO will be DC plus P, which is already given 6. So 14 plus 6 is 20. Mean diameter you can find out. After mean diameter, what you are doing is, now you have to consider principal stresses. Some students will be asking, is it principal or principal? You see here, this book wrongly it is printed as PLE, pill. Principle is like इस मतलब होता है नियम, होता है नियम जैसा, some rule जैसा principle. This is the principle. See, but here is the principal. It should be PAL. Principal stress. Principal stress means प्रधान तनाव या मुख्य तनाव है, मुख्य stress. Stress को तनाव ही बोलते हैं ना. Okay, anyway, whatever. It is principal stress, PAL stress, not PLE. Okay. Okay. So checking, we have to check for principal stresses. Okay. Now tan alpha is pitch upon pi d for single start thread. Pitch and lead are same. Okay. So pitch upon pi d. So this is equal to alpha tan inverse of pi pitch upon pi d. So pitch 6, d 17. From where did we get 17? 17 we got from the mean one, mean diameter. So from that 17, so you will get the helix angle this much, and you know that coefficient of friction 0.15 is given. So coefficient of friction mu is nothing but tan of 5. That means phi is equal to tan inverse of mu. So tan inverse of 0.15 you calculate in the calculator and you will get this value. Again you see this helix is, the angle is 6, friction angle is 8, friction angle is more. That means this is a self-locking screw. This is not overhauling screw. Self-locking screw will not automatically come down by itself. You, for bringing it down also, you need to apply force. Normally all the things in practice what we are using, these are all self-locking screws only, because self overhauling screws may cause accidents. Okay. Now the torque required is this formula, T1 is equal to W. W, not W, it is should be W1. They made a mistake here. You see here also they called this as W, whereas it should have been W1. W1, W1. So here now in this formula it should be W1. W1 tan phi plus alpha. Everything you know, you will know what is the torque. Once you know the torque, that torque we are calling it as T1, and that torque you put and you find out what is the shear stress induced in the screw. In the shear stress induced in the screw, you will find out all the values you put and see. This DC what you will put, this is the final DC. That means पहले जो कैलकुलेट किया वो वैल्यू नहीं है, उसके बाद जो ना जो बढ़ा के लिए ना वो वैल्यू, हाँ, तब टाउ आ जाता है. उसके बाद सिग्मा टी also you can find out W upon this area. So again you find out some two values. So now you can put in the principal stresses. You have two formulae in the principal stresses. One is maximum shear stress theory formula, maximum principal stress theory formula. Okay, in this you put, it comes to 61 something, and the maximum shear stress you find, you got 32, and these both should be less than the permissible stresses, and you write there because these are less than permissible stresses. Is it less than permissible stresses? Is it less? Is it less? Where is that? uh, yeah, this is 100, this is 100, both are now less than 100. So both are less than 100. One is 61, one is 37. So design is safe. Then afterwards you have to design the nut considering the bearing pressure. You find out from this equation you get n is coming to 2.22. They have rounded it to 4. Now this is too little, two threads only cannot be nut. Okay, okay, then the nut height you take as nut into pitch number. So the height of the nut or the thickness of the nut is number into pitch. Number is 4 into. Now you say, how will we know? Why not with 3? Means 3 also will be very little. Okay, you can take 4. Okay, doesn't matter if you take more also doesn't matter. Okay, okay, 4 is okay. When 2 you are getting 4, you take. Okay, then you get 24. Then the width of the nut, uh, what is the width of the nut? Width of the nut means, you know, see, actually hexagonal nut, hmm, hexagonal nut, how it looks. Okay, let me show you. Yeah, hexagonal nut, no, in one view it will be seen like this. Okay, in the top view you will see like this. No, see here, this distance will be taken as 2D, and this distance now is called as W width. That W width will be normally 1.5 times of the outside diameter. So don't worry about the width of the nut. You know, there is nothing to be designed in that. It's automatically it comes. So don't worry. This step is unnecessary. You need not write about this. Okay. So you see, just, you know, thickness of the nut or the height of the nut. This is actually height of the nut. Height of the nut, if you find out, is 24 and show, that is enough. That's all this problem. And now this length of the length of screw portion of this, you know, portion of the screw thread, you know, this is also unnecessary. Your problem stops here. Okay, that's also, I think, you know, with this we'll stop today. We have finished the power screws part of it, of this unit. Okay, and we will see about the uh, other things which are you know, screwed fasteners and welded fasteners, that we will see in the coming lectures. Thank you very much.